Hello, bug friends. Have you ever wondered what the difference between spider silk and caterpillar silk is? Well, today I'm going to tell you basically nothing, but also kind of everything. I wanted to thank my friend John Perry from the YouTube channel Stated Clearly for sending me down this rabbit hole. And now I'm going to drag y'all with me down it. So let's get into it. Let's start with what even is silk. Now, I tried to look at a bunch of different definitions for this, and most of the definitions that came back were specifically referring to silk produced by caterpillars for the textile industry, but I wanted a more broad definition and a more biological definition. So here is what I came up with and what we're going to be using for the purposes of this video. Silk is an organic protein fiber that consists of insoluble proteins ordered together to create fibrous strands. Now, generally there are two types. The first are fibrinoids, which are the proteins that make up the strands, that make up the threads of caterpillar silk. And then there are spideroids, which are the proteins that make up the strands, that make up the threads of spider silk. When I was doing research for this video, I used a book called The Biology of Spiders, which was published in 2011. And in the chapter about spider silk, they were still using the term fibrinoids when referring to spider silk, which, spoiler alert, gives you a hint just how similar in structure these two different silks are. But the word spiderine didn't show up into the literature until later. I will be using spiderines because now that terminology exists. Just note, for a long time, they were both called fibrines. I wanted to talk a little bit about who even produces silk because, again, I'm taking you down that rabbit hole with me. I'm going to pose a question to you, and that question is, out of the 30 orders of insects, and orders are big classifications, like beetles are orders, and butterflies and moths are an order, and dragonflies are in order. So there are 30 of those big groupings. How many orders or big groupings do you think produce silk in insects? And while you're thinking about that, we're going to jump into the non-insect arthropods, which is what spiders fall into. Probably the most interesting example of non-insect arthropods that produce silk are centipedes. I was not expecting centipedes to show up in my research. But apparently, male centipedes of some species produce silk in which they lay like a little sperm packet on. So surprising and interesting. But very clearly, the big players are spiders. Not all spiders can make every type of silk. In fact, orb weavers that produce the silk that you see in the spider webs that captures prey, that is fairly novel and recent in evolutionary history. And so orb weavers can produce way more kinds of silk than other spiders can. But we're going to hold on to that thought because we're going to deep dive into that a little bit as well. Did you think about that question that I posed to you? Because if you did, how many orders of insects do you think produce silk out of the 30 possible orders of insects? Yeah, if you said 26, then you would be correct, which was startling to me. Like, I knew that there were other insects besides caterpillars that could produce silk, but I guess I just never really thought about just how many different types of insects could produce it. So I'm going to talk about some of these just because I think they're interesting. And if I have to know, now you have to know as well. Many holometabolous insects produce silk. Now, holometabolous insects are those with complete metamorphosis. So that means they have an egg, a caterpillar or a larval stage, a chrysalis, a cocoon, or a pupal stage, and then the adult stage. And there's lots of insects besides just butterflies that have this lifestyle. Beetles have this lifestyle, and flies, and fleas, and lacewings, like a whole bunch. In fact, all of those can also produce silk. Surprise! Of course, the most famous example is Bombyx mori, which is the commercialized silkworm caterpillar. This is where we get all of our silk from that then eventually gets woven into textiles. It's important to note that it is just one species in the group of the giant silkworm moths. And there are other wild species that have been used to extract silk from by different cultures throughout time. The closest relationship to caterpillars is that of the caddisflies or Trichoptera, which also produce silk. But the caddisflies make their silk that helps them bind together cases and things like that. But it has to become insoluble while underwater, and it also has to stick to itself and other things underwater. And as the paper that I was reading about caterpillar silk so eloquently said, even though that caddisflies are the sister group and the closest living relatives to butterflies and moths, we know virtually nothing about their silk or their silk production. So if you need a PhD, I suppose, you have a project. Even outside of holometabolous insects or insects with complete metamorphosis, we have things like mayflies and, strangely enough, leafhoppers. We also have the web spinners, which are the closest thing to Spider-Man that we have. And if you have been following along on my What's in a Name series, which I'm going to get back to, we have already covered the web spinners. Let's talk about why you would even make silk. Because if so many different organisms are producing silk, then it must have a ton of functionality. And so let's talk a little bit about what silk does. Many insects line their homes with silk. The web spinners, for example, line the inside of the tree bark that they're living in or underneath the leaf litter. Tarantulas will spread silk all around their little homes. It's very common for spiders to just, it's soft and fluffy. So makes a little good hidey hole. You can protect your eggs or any other vulnerable life stage. So we see caterpillars making silk a lot. So if you've ever been in the eastern United States, you might have seen the eastern tent caterpillars and those big giant tents out of silk that they make to protect the larvae, but also the cocoons. The cocoon silk is what protects the cocoon on a lot of moths. The reason why we use Bombyx mori for silk extraction is because 50% of the weight of the entire pupa is just silk. So it makes sense to extract it. You can manipulate the environment, like weaver ants, for example. Also out here in the jungle, I find all the time that there are spiders that will curl like these big giant leaves and will curl them up and wrap just the outside in a few lines of silk, and that gives them a little perfect little hidey hole to hang out in. And then during the night, they'll come out and sit on top and look for prey. Caterpillars will also do this. In fact, I've gotten good enough being out in the jungle that I can tell if a spider has wrapped up the leaf or a caterpillar has wrapped up the leaf, because like the wrapping is different. But for a while, I couldn't tell, and it was like kind of fun. It was like, oh, it's a caterpillar, it's just a spider. But anyway, you can manipulate the environment and make yourself a nice little house. A big one, you can just catch food with it, especially like the spitting spider that just spits the silk out. You can get from point A to point B, just disperse. We see this with baby spiderlings, and they do a behavior called ballooning, where they'll shoot up a little silk parachute, if you will, and then float on the wind and the static electricity. But some caterpillars also do this as well. They will also shoot up a little bit of silk and then float on the wind. Safety lines are a big one that we see in both spiders and caterpillars, where you just have a long string essentially, and if you get knocked off your leaf or knocked off your substrate, then you can just climb back up that. In fact, some jumping spiders use these like bungee lines strategically when they're capturing prey, because they can capture prey that is bigger than them by grabbing it and then jumping off of the leaf. And because this bigger prey item would not have any substrate to push off against, then it's easier for the spider to sink its fangs in and deliver the venom and just wait for the venom to do its work, instead of being like kicked and thrashed about by something that isn't hanging in midair, essentially. And then when the prey is dead, the jumping spider just up that little safety line. Basically, silk is just strong and soft, so you can see how it would be really versatile in the different kinds of things that you could use it for, especially if all you need to do is change its elasticity or its strength a little bit. Then that gives you a lot of options to be using this silk for. Where is silk produced? The web spinners, very interesting, are the closest thing to Spider-Man and just shoot it out of their forelegs. And also, fun fact, they produce the finest of all insect silk. Caterpillars produce their silk in modified salivary glands, essentially. So in the caterpillar head, you have the labial glands. And the labial glands in most insects produce saliva and spit, but in caterpillars instead produce silk. This is really common in biology in general. It's a lot easier to take a structure that already exists and modify it to do a new purpose than to invent a whole new structure to begin with. In spiders, the silk comes from the other end. On the abdomen, or the butt end of the spider, you have spinnerets, which are specific structures of where the silk is coming out of. And on those spinnerets, you have spigots. And each of those different spigots are connected to different glands within the spider. But that is where the silk is coming out of and being produced. Not all spiders produce the same kinds of silk. Not all spiders can produce all of the silks. And so in this video, we are going to be looking at orb weavers as examples because they are the most evolutionarily derived. They have the most silk options and they have the most sophisticated types of silk, and they can produce the most kinds of silk versus something like tarantulas that don't have as many silk types or options. Also, orb weavers are like the most studied. So that's what we're going to be going with. Orb weavers also have the strongest silks out of all of the spiders. Now, let's look at what some of these silks are and what they do. These 6 different types of glands can produce many different types of silk. Now, these are not all exclusive to the orb weavers, but I will mark the ones that are exclusive to orb weavers with a little star on screen. Some silks that can be produced include like silks to wrap up egg cases. Female spiders produce those kind of silks. You have the sticky silks, so that way you can capture prey. You have dragline silk, which is the strongest, and that is what the spider attaches its sticky silk to. So the draglines are essentially just like the scaffolding so that the rest of the web can be built on it. Similarly, we have this silk that makes the stabilimenta, which if you've ever seen like zipper spiders, for example, is that white kind of zigzag pattern in them, or sometimes you can find them in the shape of an X going through. There's lots of theories about the stabilimenta in general and what it's used for, but that is beyond the scope of today's video. And then finally, you have this really fine, almost invisible to the naked eye kind of silk that attaches regular silk to the substrate. So if you're building your web or whatever, and you're gonna stick it to a leaf, this anchor silk helps stick it to the leaf. Or if you're making these like parachuting or these drag lines, and that's what sticks it down. The maximum number of glands you can have is found in the orb weavers, and that is 6 glands. Similarly, not all spiders have the same amount of spinnerets either. The textbook example is that spiders would have 3 pairs of spinnerets, the anterior, which are first, the medial, which are in the middle, and the posterior, which are at the bum end. But not all spiders have all of these spinnerets. And that's actually how you can identify some families of spiders, is which ones are there and the pattern and the shape of them. Those spinnerets are then attached to the spigots that would be attached to the different silk producing glands within the spider. There are a ton of spigots that are covering the spinneret. For example, A. diamadatus has 1,300 spigots that are covering all of its spinnerets. While insects can only produce one type of silk at one stage in their life, pretty generally, spiders can produce all of these different types of silk at almost every stage in their life. Spiders are very versatile in what types of silk and when they can produce those kinds of silk. Let's look at the similarities between the caterpillar silk and the spider silk. I am not a chemist, so I'm not going to be throwing a whole bunch of chemical names at you. I just want you to look at these structures because they are essentially the same. The way we get there is a little bit different, but basically silk just kind of looks like silk, regardless of who makes it. Beta sheets are made out of crystallized amino acids, and these are what give the silk its strength. In between all these beta sheets, you have alpha helices. This is called the amorphous matrix, and that's what makes the spider silk stretchy and flexible. So the more beta sheets you have, the more crystals you have, the stronger the silk, but the less elastic it is, and vice versa. So if you have a lot of alpha helices in this amorphous matrix and fewer beta sheets, and you have silk that is a lot stickier and a lot stretchier. This amorphous matrix makes the silk super stretchy, and in some silks, you can stretch it 300% before it snaps. Some orb weaver silk can be stretched 80 kilometers before it would snap under its own weight. Silk is liquid when it is produced, and then it needs to be turned into an insoluble form by the creature that is producing it, and that process is irreversible. So once we go from a liquid to a solid, like that's it. No going back. In spiders, we're not really sure what that process is, but in caterpillars, we know that you can go from the alpha configuration to the beta configuration simply by tugging on it, and that is enough to get it from a liquid to the insoluble state that is silk. If you look at the structure of silk between spiders and caterpillars, they essentially look the same. You have either spiderines or fibrines, which are bundled together to make the threads of silk. This means that spiders and caterpillars essentially converged on the same structure. Why? Because it works. This is an example of convergent evolution. So basically, spiders and caterpillars are not closely related at all, but they have come up with the same solution for making silk. This would be like, I like explaining convergent evolution like you and me, we're both in math class and the answer is 42, and we both get 42 as an answer, but we got there using different methods. This happens a lot in biology, and a lot of times the structures that just work are oftentimes converged upon. So silk, the silk structure, works great. So both caterpillars and spiders got there. Hello, this is Future Editing Nancy, and Future Editing Nancy thinks that past Nancy could have done a much better job explaining the differences between caterpillar and spider silk than she did. So we're going to try again. Because spiders and caterpillars have functionally converged on silk production independently, there are a lot of similarities, but there are some differences. And to kind of help explain these differences, especially because convergent evolution can be a little bit of a tricky topic to wrap your mind around, I am going to use an analogy. Not the perfect analogy, no analogy is, but let's work on this together. So my analogy is that both spiders and caterpillars want to build a house, like in The Sims or something. However, to explain this convergence, right? If you looked at a house, you'd be like, that looks like a house. But you could start to see little differences that make up these houses. So let's say caterpillars hired one architect and spiders hired a different architect. So we'll be able to see differences in style, we'll be able to see differences in building materials and the amount of building materials, and we'll be able to see differences in the blueprints. So we're going to be using all of these to talk about blueprints, the genetic code, building blocks, the amino acids that are making up the proteins, the amount of these building blocks that we're using, and the different proteins or the different styles or the different pieces of the architecture together. Here are a couple caveats because this is biology and it's messy. Genetic code is really difficult to parse out in both spiders and caterpillars because there are so many iterative and repetitive chunks that it's just difficult to decode. Some of the proteins, we don't even know all of the genes that make up those proteins. We just know what those proteins are made out of. For simplicity, we are going to be comparing caterpillar silk because each species of caterpillar can only make one type of silk. That is in direct contrast to spiders, that one individual can make tons of different types of silk. So to make this comparison a little bit more simplified, we are going to be comparing individual species of caterpillar and the silk that they make to individual species of spider and the dragline silk that they make. So the dragline silk is the drag lines, as its name might suggest, but also is what makes up the non-sticky frame of spider webs. Let's first start with just the overall structure. Like we talked about with the similarities, there are a ton. It's basically just a bunch of these stringy proteins wrapped up in a sheath. So they are functionally very similar. They're structurally very similar, but there are enough differences to note. So let's just look at some of these little differences. The first is that we can see little differences in the architect's style when we look at the structure of silk. Spiders have spidroins. Those spidroins are bundled together. They are covered in a skin, and then they are covered in a protein sheath, and then they are covered in a fat, bigger sheath, essentially. Caterpillars have two bundles of fibroins together. Enveloping each of those different bundles is a protein called sericin, and then that whole thing is in a big protective protein shell. And that's what makes up the silk of caterpillars. So again, functionally the same. You've got the stretchy bits in the middle and a nice protective casing. But exactly what that casing looks like, you can start to see the differences in our little architects. We are first going to take a very narrow lens. We're going to start with caterpillars, and we're going to start with closely related moth caterpillars and zoom out, looking at different proteins and different building blocks. And then we're going to be looking at spiders, different spider species, and zooming out. And then we are going to look at spiders versus caterpillars once we have a little bit of an idea of what we're looking at. This table is looking at heavy chain fibroins, which is just one type of fibroin protein that you can find in silk. It's looking at the heavy chain fibroin chemical makeup. And looking at this, you can definitely tell that they're made by the same architect, or they are being produced by the same line, the Lepidoptera line, the butterflies and moths. Here we are. Because you can tell that there is like 50% similarity even between all of these different species. Even though overall you can tell that we're in the same Lepidoptera line, we're being designed by the same architect, we have over 50% of the same types of chemicals going into making these heavy chain fibroins, that we still have like considerable difference. If we broaden this out a little bit and add different species, we have a butterfly species in here, which is now highlighted as well. You can see that we still have a lot of conservation. And what we're looking at here are light chain fibroins, which are just another protein that make up the silk. And you can see the amino acid sequence that is going to be making up that protein. So the individual building blocks that are making up that protein. And you can see here, there's still a decent amount of conservation, about 50%. But again, you can see that there are significant differences as we look at all of these different types of caterpillars. Heavy chain fibroins and light chain fibroins are integral in the construction of the silk. So we would expect to see a lot of conservation in these areas because you need them to make silk. Another important core protein is the P25 proteins, but we find a lot more variation in these proteins within silk. And here we have, again, different species of caterpillar. And now you can really start seeing the differences that emerge when we start looking at these P25 proteins. Instead of just looking at the sequence of amino acids, or essentially the code that makes up these proteins, we can also look at their molecular weight. So we can see how much of the silk is comprised of each of these different building blocks. Each amino acid is like a building block. So in some silk, you might find that we use 25% of one building block, but only 1% of another. That's what we're looking at here. You can see among these different species, you can see that in these building blocks, different amounts or percentages of the overall weight of these building blocks are being used to create the silk. Some notable examples are alanine, glycine, and valine. We have a good idea of what we're looking at in caterpillars. So let's move on to spiders. If we look at spiders, we can see that in between different species of spiders, their amino acid sequences that make up the spideroin proteins are different. And then if we look at the composition of amino acids, so the amount of building blocks that are going into each of these proteins, you can see that they are also different between different species. Again, the sequences between different spider species are different, but they've got kind of like the same vibe going on. You can tell that these were created by the same architect or in the same lineage of the spiders. When we look at Bombyx mori, we can see how many more iterative chunks there are as compared to the spiders. And we can see just how much longer that sequence is of amino acids that are making up the proteins versus that of the spiders. Now, if we look at the amino acid compositions that are making up the different kinds of silks, again, you can see different ones are being used and also at different percentages. I want to bring your attention to glutamine, glycine, alanine, and serine specifically, and you can really see the differences between the caterpillar silk and the spider silk. So rehashing our analogy, as we look at different architects, the spiders or the caterpillars, we can see how they are different from each other in just the structure, the style of the silk when it's produced. But we can also see it in some of the little details, including the blueprint, the genetics for creating the proteins, the sequence and length of and code of making those proteins via the amino acids, and the amounts and types of the building blocks or amino acids that we're looking at. So there you have it. At the end of the day, you still get silk, but the nitty-gritty details of how you got there were a little bit different, not just between our major groupings, but also individually between species within those lineages, even closely related species, because every species has its own unique needs. So now on to the commercial importance of silks. What are we using silk for? What possibly can we use it for? Right now, Bombyx mori is the only commercial source of silk. And if you buy silk textiles, that's where that silk is coming from. It was caterpillar spit, essentially. As I mentioned before, the pupil weight, half of that is silk, which is why it is so commercially viable. We did make a textile from spider silk. It is absolutely beautiful. It's from the genus of the golden orb weavers, and so the cape came out a really beautiful golden color. However, it was quite difficult. It was no easy feat to do this. The spiders were wild caught from the mountains of Madagascar, and it took 20 years to make this cape. So stare at this image a while because it took a long time. Silk was extracted from 24 spiders at a time. People who were working on this would go up to the mountains, collect 24 spiders, come back down, wait for them to make the silk, harvest the silk, and then take the spiders and put them back. And then the next day, they would collect 24 new spiders. Get ready for this. A total of 1.2 million spiders were used to make this cape. So please continue staring at it. While this is a really beautiful work of art that even pays tribute to the spiders that made it, no commercially viable option for spider silk currently exists. We can get microbes like bacteria to produce spider silk proteins. We can even get goats to produce spider silk proteins, but the spider butt seems to be a very integral piece of the process to go from proteins to actual silk. But perhaps in the future, when we can make it viable, there are some interesting applications for it. Dragline silk produced by spiders can be infused with metal ions. Normally, there are hydrogen bonds that are keeping the spider silk together, but when treated with metal ions, those bonds become way stronger, and it takes 10 times the amount of force to break spider silk with metal ions than it does just regular spider silk. We can also use spider silk to reconstruct nerves. So hopefully in the future, if someone is suffering from nerve damage of some kind, we can use spider silk to encourage the connection between different neurons. Caterpillar silk also has some interesting biomedical properties. For instance, it's antimicrobial and antibacterial. We have not yet found that to be true for spiders. So in summary, here are the similarities and differences between caterpillar silk and spider silk. Their similarities is that the structure is the same. You have protein strands which are bundled together to make the threads of the fiber that's going to be silk. Caterpillars can only make silk at one life stage and can only make one type of silk, versus spiders that can make a lot of different types of silk and at pretty much every stage in their development. Caterpillar silk is made in the labial glands, which in other insects is used to make spit, versus Spider silk is made out of their butt on spinnerets and the spigots that are on those spinnerets. There is one modified labial gland that makes the silk in caterpillars versus up to 6 different glands that can make silk in spiders. The mechanism to take silk from its liquid form to its insoluble solid form is known in caterpillars. You just tug on it, but unknown in spiders, and so probably has a different mechanism. Caterpillar silk proteins are called fibroins, and spider silk proteins are called spidroins. Caterpillar silk is antimicrobial, so antibacterial and antifungal, but we have not found that to be true, at least for the spiders that we have studied. Spider silk is stronger than that of caterpillar silk. And finally, caterpillars, especially that of Bombyx mori, are domesticated and commercially viable, and we have not yet domesticated any spiders, and their spider silk, unfortunately, is not yet commercially viable. Well, bug friends, I hope you had so much fun learning about silk. I knew nothing about silk when I got started, so I really wanted to thank my friend John Perry from the YouTube channel Stated Clearly for asking me about this, because literally he asked me and I was like, I don't know. And thank you to everyone who submitted questions. I have hopefully answered all of them along the way to the best of my ability, because sometimes the answer was, we don't know.